How the Sausage is Made, Part 3. File types in Photoshop. The native file type of Photoshop is PSD, stands for Photoshop Document. It can open, edit, and save a variety of other file formats. Mostly for print, we're working with PDFs for final output. TIFF files are kind of like an older format that you might run into from time to time. JPEGs, obviously, everyone knows from digital photography. And those are all formats that it can save to. For the web, we're mostly, once again, looking at JPEG, and then a modern format called PNG, which we can take a photographic image and have remove the background and make it transparent. And a lot of web design uses this to get away from like a boxy look. So you have objects that are images that are various sizes, and they're cut out and they can show the background of the web page through it. GIF also has transparency, but the transparency is very limited compared to PNG. So if you do have the choice, just move forward with PNG. But know that there are still a lot of GIFs on the web. So where does color come from? Well, let's talk about the different systems that we have. RGB refers to red, green, and blue. CMYK refers to cyan, magenta, yellow, black. And black, I mean, we can't use B because that's already been used. It turns out there's another term for black in the printing industry, and it's called key. So we used to print key lines around an image so that it would hide any potential misregistration of the plates when we're printing cyan, magenta, yellow, and black plates all together. We just have that key plate that makes a box around the image so that if there's a little misalignment of any of the colors, it won't show up because the black or the key color will cover it. Grayscale is just what it sounds like. It's from white to black and all the shades of gray in between. So let's talk about RGB. Now, this is the color space that we normally deal with computer monitors, but it's the weird one. It's the one where it doesn't work the way that we remember color working in elementary school when we're working with paints. It's known as an additive color model, and it describes how light produces colors. So this light could be LED behind your computer screen that shines red, green, and blue pixels in different intensities to simulate different colors. And you'll see that when we mix these colors, they produce other colors. But it's not intuitive. So for instance, in this graphic, we can see when we mix all three colors together and where they intersect, that produces white. However, when we mix just red and green together, counterintuitively, that makes yellow. That doesn't make a lot of sense. But that's just how the additive color model works. So it kind of works the opposite ways that you would mix paint. I created this graphic in Photoshop itself. Each shape layer is set to a blending mode of screen. That's some information that will make sense later. On the other hand, the CMYK refers to the subtractive model. And this is what we're used to when we're painting in the real world. When we take paint and we put it on a canvas, this is actually the model that we're using. It turns out you can generate infinite numbers of colors just from 3 different pigments. We use cyan, magenta, and yellow. And when you mix them together, look at the intersection. We get those red, green, and blue colors from the other model. So these models are actually kind of a mirror of one another. What the subtractive model does is it takes a white substance, like a canvas or a piece of paper, and when you apply a pigment to that substance, it is blocking light from being reflected back at your eye. And so this is actually subtracting the wavelengths of light that reach your eye by applying a pigment. And when we mix these pigments together, we get different colors. So cyan and magenta make a nice blue, and magenta and yellow make red. And then we obviously have, we would think of it as blue and yellow make green. Well, it's close enough. But you see that these are our red, green, and blue colors that are in the other color model. And if you look in the center, you'll see that we have this kind of murky, dark color. It's not exactly black. It turns out pigments aren't 100%, effective. They are not super effective. So we need to add a fourth color in order to produce the darkest black that we normally see. And so that's why we call it CMYK. So when we apply the black ink, suddenly we have the whole spectrum of colors on the printed page. Now, how does Photoshop handle color? We have to think of three different aspects to understand how color works in Photoshop. We already talked about color modes a bit, and we'll talk about bit depths and gamut. So the different color modes in Photoshop that are available from different menus are RGB, CMYK, Grayscale, and LAB, which is pronounced LAB, not lab. LAB is a color mode where Photoshop uses this color mode to convert from one color space to another. And it turns out there's advantage to using this mode because the other methods of making color describe how you actually make the color. They don't describe what the color really looks like. So RGB, you're mixing intensities of light. CMYK, you're mixing intensities of pigment. But the LAB model refers to how light or dark a color is. And then we have two axes, an A and a B axis. A is from red to green, and B is from blue to yellow. And it turns out this provides us with a space that makes it very convenient to transfer from one color to another. So we move it into the LAB space first, and then we can move it into a different color mode. Directly going from one color mode to another involves more complicated math. So this is not something you necessarily need to worry about, but this is something that Photoshop is taking care of behind the scenes. There's also indexed color, which is an older kind of color mode. Older computers used to not have enough memory to handle high color images. So they used a hack. They produced a table, and each table was indexed to a certain color. And so you just say, turn on this pixel and use the color that we've defined in index 3. And it goes that for every pixel in the image. So it saves on memory, and also it, as a side effect, limits the number of colors that you can produce. GIF and PNG images have index color as a possibility. PNG images can also be 24-bit, but there is a version of PNG that uses 8-bit, and that would be the index color version. There's also multi-channel, which is a production format. We're not going to really work with multi-channel because it is doesn't offer layers, and so it's like when you're making a final product. You use multi-channel to get special effects. So just know that it's there, but we probably won't use it at all. Duotones used to be very popular, but most of the time when we see a duotone, we think that's like an old-timey image. It's actually a nice effect. Basically, it is a grayscale image, but it has color in it because you're using multiple pigments to represent the span of colors from light to dark. So you have maybe black is taking care of all the shadows, and then you use a dark brown color that will represent the midtones up to the highlights of the image. And these pigments can actually overlap, so they're both representing the same thing at the same time, and they fade into each other. So it produces a continuous tone image that actually has more kind of continuous tone than just producing this with black ink would produce. That's one of the main reasons why they use duotones, is because it would allow them to give, you know, the more definition between the lights and darks. And it also made it, yeah, it gave a nice effect. It turns out you can use 2, 3, or 4 colors to make duotones, and that's available from this color mode. Bit depths. Mostly in Photoshop, we're working in 8-bit, which, wait a second, 8-bit, that sounds like those old computers from the 80s. We say 8-bit, we mean 8 bits per channel. So essentially an RGB image is using 8 bits per channel, so 8 times 3, it's actually 24 bits. This produces more colors than we can actually see. 16.7 million colors are available in the 8-bit space. 16-bit, even more. I don't think dolphins can even see this many colors. 281 trillion colors. And then we have something called 32-bit. Think of 32-bit as basically like 16-bit, but with f-stops. If you're into photography, you'll know what that is. But basically, it just gives us even more flexibility when dealing with HDR, or high dynamic range photography. A bit more about bit depths. So, like I said, 80s computers were limited. So they usually had much less than 256 colors. The original computers only had 2 colors, black and white. So it's 8 bits total, not per channel. And so obviously this is indexed color. But what does that look like? Well, let's take a look. Here we have an image that I've converted to 1 bit. And so we just have 2 different colors. One is representing the lightest parts of the image, and one is representing the darkest part. It's kind of hard to tell what this is. So let's add some memory to our Commodore 64 and see if we can get a bit clearer image. So let's go to 2 bits, which gives us 4 different colors. Oh, okay, so we see we have like a, it looks like a cliff or something, and I'm not sure if that's water behind it or if that's the sky. So let's take it to 3-bit. Okay, yeah, that's definitely the sky. And we're seeing, you know, our first problem here is we can kind of see some definition. There's some greenage in front, but the sky, that's not how skies normally look. There is some definite banding between the colors of the sky. One thing that people don't really realize is the sky is always changing. No part of the sky is the same as another part of the sky. So it has a wonderful expressiveness to it. And so it's really nice to look at in photos when you have a good sky and it's not cloudy. It just makes things look so dynamic. In this photo, we're having a bit of a problem representing that sky because we don't have enough colors to work with. So let's try moving it up a few more bits. 4-bit, okay, we get a more definition in the foliage. 5-bit, we're starting to get some definition in the sky, which is looking good, but we still have that banding. 6-bit is, the banding is starting to get taken care of. 7-bit, we're almost there, and we're about to reach the limit of old-timey computers. So here's 8 bits, and it's indexed, and darn it, we still have that banding in the sky. If only there were a way we could fix this. There is. 24 bits. So adding more memory to our computer and 8 bits per channel. We now have a bright, vibrant image where we can tell what everything is, and the sky looks beautiful and wonderful, and we can see the foliage in beautiful detail. So, gamut. Gamut is basically us throwing up our hands and saying color systems have their limits. That gray splotch is showing us all of the possible colors. The triangle inside the splotch shows us the colors that the human eye can see. Different animals can see different wavelengths of colors. Some are more limited than humans, others are beyond what we can see. But this is basically the limit of human vision. This doesn't represent the saturation or the lightness of these colors, just the hue. So just think of it that way. It's just a abstraction of the total colors, not the actual total colors themselves. Turns out we have a few different color spaces that we would normally work in. We have 3 that are in RGB, and then we have a CMYK space that's pretty normal for us. These color spaces overlap, and these overlaps have their consequences. Most of the color space that we use on the web is called sRGB, and it's represented by this black triangle, which doesn't represent all of the colors that we can see with our eyes, not even close. And then if we want to go to a slightly bigger color space, we can use Adobe RGB, which is the blue triangle. It's getting closer to all the colors that we can see. And if you're a pro photographer, you're probably using, in this modern era, Pro Photo RGB, which is very close to all the colors that we can see. Actually goes outside of the colors we can see quite a little bit on the edges there. The important thing to remember about all these color systems is that they're all using the same number of bits to represent different colors. So that's why when we convert from one color system to the other, we need to have some kind of mediator. So that is why we use the labs, LAB. Oh goodness, I said the wrong word. The LAB color space to convert from one to another. Even if it's RGB, you'd think, oh yeah, RGB, the numbers stay the same. Well, if you're going from sRGB to Adobe RGB, if you plot on that little color blob, it's going to use different numbers to represent the same color. So that's why it has to go through, you go through the LAB space first. And that will give you an approximation of what that color would be in the other color space. CMYK is obviously, that's the trickiest one. Adobe RGB covers most of the CMYK space. And obviously you can see there's a great deal of colors that are outside of the CMYK space in the green areas. So very vibrant green colors are just not possible for us to reproduce using those 4 colors in the printed page. So when you're looking at your screen in Photoshop, just keep in mind that not all the colors will be printed the way you think they are. And you can proof that. There's an option to proof that in Photoshop. We'll go over that later in the course. But yeah, just keep in mind that not everything you see on screen is going to be possible to reproduce.